So in our last video we learned about how to build a basic CNN model, and now it's time to improve our score more here. Okay, so we get here less training loss. So konnichiwa friends, my name is Asma Sumasi and welcome to day 4 of the deep learning bootcamp music genre classification. So welcome to day 4 of the bootcamp. In this video we will learn about deeper models and how to make higher score and how to submit the final model. Okay, so this video will be all about how to increase your score and lower your loss here. Okay, and also I may or may not submit the final model in this video. Okay, maybe. So for making my video speed, my epoch will be 1 to 4 length. Okay, but you should take your epochs to 20 to 60 epochs. Okay, for your training loop. Also tomorrow we'll be knowing on how to make our validation dataset and tracking validation along with connecting your WAN-DB to your log results. Okay, so tomorrow video will also be helpful for you. So now we start with what will work for our score increasing and what will not work. Okay, first thing is that data normalization is the most helpful thing you could think of. Okay, CNN trains far better and more reliably with normalized input. Okay, so instead of our 0 to 12, if we are having 0 to 10,000 large extreme dataset, it will be failing the deep learning model here. Okay, so normalization help. Then we have strong data argumentation. Basically it's help models use many audio samples so that it generalize well here. Okay, then we have more calculation depth. So basically the convoluted layer one after the other stacking, and it will learn richer acoustic patterns that small models may fail. Then we have proper learning rate and a scheduler here. Okay, so many trainings failures are learning rate problems, not your architecture. Okay, because machine learning and deep learning is a gradient issue here. Okay, so using proper learning rate and a learning rate scheduler we could solve it. And finally may or may not you could use your large training data set to scale strongly here. Okay, now the next we have what will not work here. Okay, for your score increase, first thing is that training longer or using more epochs will not help. Okay, so don't train more than 20 epochs, and I would say finally 30 to 80 epochs is your max here. Okay, unless your score is actually increasing after each epoch, I will not recommend to increase the epochs here. Okay, mainly the model matters, not the training here. Okay, if your architecture and your optimizer was perfect, longer epoch will not be necessary. Then finally using huge batch size here. Okay, and it greatly affects the final generalization. Okay, so if you are using very huge batch size, let's say the common is 32 to 64, but if you are using very large batch size, it will greatly affect the generalization. Okay, then finally we have here high male resolution or your sample rate. Okay, because it often worsens the model due to noisy features, large memory and harder learning size. Okay, same for the sample rate. Then next we have here is extremely large kernels or extremely large CNN models. Okay, for first of all, large kernels are often slower and work worse than the smaller kernels. Okay, and also the CNN model, if you are making it large, it could increase the chance of overfitting. Okay, you should have max 4 to 6 convoluted layer in your neural network. Then finally increasing the connected layers. Okay, basically the linear layers will not help here because the convolution is the learning source. Basically the convoluted layer will be learning the patterns here, and the linear layer is only for your intermediate to get the values. Okay, I would recommend 1 to 2 linear layers only. Then we move on to our data augmentation, which is basically an artificial way of increasing the training dataset by applying transformation to existing samples here. Okay, so we are giving the samples here, and for reducing our fitting and improving our generalization and help CNN learn invariant features, we use our data augmentation on our training sample to get more dataset here and the model learn better here. Okay, it is divided into two types. One is our audio segmentation and second is spectrogram segmentation. Okay, in our audio segmentation we transform our audio here. Okay, so first we have here is our time shift, which basically shift the sound slightly forward or backward in time, so by which the model become robust to time differences. Okay, so by using this time shift, our model will be robust to any time difference that is happening in our test audio. Okay, so we do by here, we basically use here random dot int to get a random number for our time shifting. Okay, so since we are using random here, we should also stop random size here, which will be talking in my next video. Okay, so for now we use our shift to get a random int, and that random int will be using our np.roll, which is taking our sample rate, and here we will be shifting our audio from forward backward here. Okay, so this is our architecture. We'll be making a new variable named argument, because only training data will need argument here. So we will run it, and here before our padding here we will be doing our argumentation for our audio only. Okay, so for this one is my audio here. I will run this code inside this here. Okay, so when you will be running this code, the audio you get will be well time shifted according to random here. Okay, then next thing we could add here noise here. Okay, so for example we could add here a small Gaussian noise or an environmental sound, which will basically stimulate our real world recording here. Okay, so by adding Gaussian noise or any environmental sound here, our model will now become robust to any noise or any environmental background sounds. Okay, so that's why we'll be stimulating real world recordings in this part of the data augmentation. Okay, so we do this by using the same way. First using the random to get our random noise from our length of the audio is float, and then the noise we add it with our audio here. Okay, also you could use this with our time shift, or you could use it alone. Okay, so you could use one or both augmentation. Okay, next we have pitch shift here. We slightly change the pitch of the audio file here. Okay, so our model could capture the instrument variation with this augmentation method. Okay, we slightly change the pitch of the incoming audio files so that the model could catch the instrument variation in the audio file. Okay, so we get a random uniform or continuous value from -2 to 2 here, and then we add it to our audio using librosa.effect.pitch shift here. Okay, it takes our audio, then our sample rate, and finally the end steps, which is basically this step of the pitch shift here. Okay, so we could then add it with other augmentation methods here. Okay, so let me add the comments here, and next we go to our time stretch here. Okay, basically it speed up or slow down the audio so to capture any variation in the speed in the test file here. Okay, so basically it adds a generalization here without changing pitch or sample rate here. Okay, we could do from 0.9 speed to 1.1 speed. Okay, generally the music lies under this, so we get in continuous random variable from 0.9 to 1.1, and then using librosa.effects.time stretch we add it here. Okay, so this is the final augmentation method which you could do before converting the audio to spectrogram here. Okay, next we have here is our audio segmentation, where we'll basically change our audio here. Okay, so audio segmentation is done here. Next we have our spectrogram segmentation, where we'll be changing our spectrogram here. Okay, so we do it by two things. First is that we add time masking here or the frequency masking. Okay, so basically in time masking we amplify the x-axis, where basically we hide one signal from the audio image. Okay, basically it hides a vertical region from the audio file, so model become robust to any time masking which was done in audio. And in frequency masking we invariate our y-axis here, which randomly hides a signal horizontally. Okay, so by this the model will now will be robust to our frequency. Okay, so we do this by using this same method which I provided, and it is done after we change to our spectrogram image, where we first, let's add the comment first and this space here first, let's delete it, and then after our power to decibel will be adding our augmentation here. Okay, so we added the time masking here after we converted the audio to spectrogram here. Then we could use our frequency masking here to convert our spectrogram image here. Okay, so this is the final code here for data augmentation. When we'll run it, we pass the arguments through here and we make a new argument here. Just a second, we add a new self.argument here, which will be taking our self.argument, and it is the one which will be printing here. Okay, so you will see that here the torch type return the same masking here. Okay, so by this your whole return statement is true here. Also remember that after you do the whole pre-processing, you must mail db.tensor.unsqueeze here, and then you normalize here with our standard normalizer. Okay, so we minus with our mean and then divide by our standard deviation plus a small value, so we don't have divided by 0 error here. So we write the whole function and we'll be returning this value here. Okay, the mail/db, and we'll be running it. You will see the final size here which we have written previously, but now our data is augmented and normalized. Next we have is the optimizer here. So the first thing you could do is that you could use your AdamW optimizer, which is an optimizer which generally used in our transformer path, but since we are making a big model here, you could use AdamW here. Okay, and for the learning rate here and the weight decay same as 1e minus 4 here. Okay, so a very small learning rate, and it will help us prevent overfitting, and it have very more stable training curve. Okay, but generally we use Adam only, but with our learning rate scheduler. Okay, this learning rate scheduler help reduce our learning rate when the validation stops improving here. Okay, so we have here a optimizer curve where a large learning rate could do a zigzag motion in our gradient descent, and if you have a very slow learning rate, the learning eventually will be very small and the gradient will be stop increasing. Okay, to solve this error, we have our learning rate scheduler which will be taking dynamic value for our learning rate here. Okay, so the learning rate will change and lower depending on the scheduler here. Okay, so we define with our torch.optim.lr scheduler, where we use your reduce learning rate on plateau scheduler here. Okay, so by using this method, we basically import an scheduler in our training loop. Okay, so now we use the optimizer.step as usual, but basically outside the loader class here and inside the training loop we basically call scheduler.step here. Okay, and then we pass the loss which we want to reduce here. Okay, so here it's not verbose here. So basically outside our loader here we use here scheduler.step here, and inside we pass the loss here which we want to minimize here. Okay, so we want to minimize our total loss here for our each loader, and we will be using scheduler.step here. Okay, and to print the current learning rate of inside the loop here, we basically use optimizer.parameter groups of our first learning rate here. Okay, and so when we will be printing this, you will be getting the learning rate on that period of time here. Okay, so we use our reduce learning rate on plateau to have a dynamic learning rate. Okay, next we have our early stopping, where basically stop the training if model stops improving. Okay, so we do it by creating a new variable which will store the base loss here, and then we have our patience here and the counter here. Okay, so the patience, so we create a new variable in epochs, and then our patience and then our counter equals to 0, and here basically if our the total loss is less than our base loss here, so we'll be using base loss equals to total. So basically learning is taking place, and here we use our counter to 0, else the learning is not taking place. So we'll be increasing our counter till our patience level is reach here. Okay, so here training total is more than base model, so here learning is not taking place. So here if the counter is more than equals to patience here, then we exit the loop and we call here yearly stopping is reached here. Okay, then finally we have our label smoothing in loss here, where basically we add an label smoothing curve inside our loss function. Okay, it basically reduce overconfidence and help us in smooth gradient curve. Okay, so here we add it by using label smoothing equals to 0.1. okay, is 0.1, so that we add in label smoothing of 10% here. Okay, so this one is also done. Now inside the model on what we could do. Okay, so the first tip you will use is to use nn.Sequential to basically stack the neurons together. Okay, so you will see here that instead of creating new variable for our one layer, we stack them together in our nn.Sequential here. Okay, so we could delete all this, and here we create a new variable named nn.Sequential, and here inside it we could stack the neurons together here. So we could add here neurons one by one on what we had learned in our previous video. So we could do this for all our, and here we could pass only this variable here. Okay, so by using our self.sequential we could lower the case here. Okay, then we have a leaky ReLU instead of ReLU here. Okay, so we have here ReLU function, where instead of ReLU we could use our leaky ReLU for our activation function. Okay, we could go from 0.05 to our 1 here depending on the size here. Okay, then we could use here deeper convoluted layer, where basically we have used only 2 layers here. We could increase it to more layers using our kernel size equals to 2 here, then another convoluted layer with our kernel size equals to 3 here. Okay, so we could increase it one by one to get the final value. Okay, so we could also try to learn more than 3 or 2 more than 4 here. Okay, but remember that if you are using more than 4, you may risk overfitting. Okay, so this now network will now the edges, harmonics, rhythm pattern, etc. Okay, then we could add here is that we use our dropout layer going from 0.2 to 0.4 here. Okay, so after each layer we could use our dropout layer starting from 0.2 to the very last 0.4 here. Okay, depending on the layer here, and then finally we could also increase our kernel size starting from 2 to 3 here. Okay, so this is basically how we'll be improving our model here. So finally you will see here that this is my final CNN model, where I use my self dot, let's say here, feature, which is a sequential layer of convoluted layer, where we pass many convoluted layer one after the other with our batch normalization, followed by our leaky ReLU, then max pooling and dropout layer after 2 convoluted layer, and then we do it again, and finally we have the same architecture, and finally we do it again with ending with our max pooling layer for our this convoluted layer. Okay, so in between we have our adaptive pooling 2D, and then we have our classifier layer, which is also a sequential layer, and then we pass our the convoluted layer whole sequential layer, and then we pass the pooling layer, which is our adaptive pooling, and then we use our x dot toss dot flatten to differentiate between our convoluted layer and the final linear layer. Okay, so it flattens, and finally we use our self dot classifier for our final prediction layer. Okay, here we use our leaky ReLU and our dropout function. Okay, and here you will see the leaky ReLU values are going from 0.1 and is increasing after each layer here. Okay, to 0.4. So basically this is how we increase our model size, kernel size, and our dropout layer to finally get a deeper model here. Okay, so finally, the secret in deep learning and machine learning is experimentation. Okay, so you may use one or all data augmentation, which I told you, or for the training loss you could use more deeper models, or you could remove layers here. Okay, but don't change our smooth learning here and the yearly stopping here. Okay, so here main thing here is that you could change here to more deep learning models, or you could change here the data augmentation. Okay, so finally do experiments, and tomorrow we'll be learning how to use our validation loader, connect the WAN-DB and submit the result. Okay, so today as a homework, do experimentation with one of the data augmentation and the deeper model which I provided. Okay, for our optimizer yearly stopping, please don't change it. Okay, it is already professional level. Okay, so this video cover the deep learning model and how to make more high score using our data augmentation. Okay, so that's all for today. Thank you and bye bye.